Hello, everybody. So tonight starts week 6 of 6 out of 8. So we are getting very near the end. I like to front load the courses so that when we get near the end, since pretty much all the SDEV courses have a major project involved, the workload should get a little bit lighter as we approach the end. I do kind of set them up on purpose that way. Tonight's the night that I mentioned the very first day. There's the one night that we can't really split up. Data structures are on the major learning objectives for all the junior level courses. And well, in classroom, it's rare that we use them in the classroom. This is something that is more long-term application. So a lot more pictures on the board and talking about stuff. We're going to start with a couple examples, 3 examples. We'll look at some making stacks and queues and binary search trees. And then we'll talk about a bunch of other ones. And we'll be here for a while. Probably 9:30 was the original plan, but I have been here since 8:30 this morning. So, yeah, I'm going to be very, very tired by then, but we really only have one day to cover data structures. And it's a very important thing in software development, but in general, it's also a time-consuming planning, strategizing thing that of the sorts we don't have much time for in the classroom. So it's
I'm student. À la fois beaucoup d'argent, voilà ce qu'elle a fait pour moi.
future. Oh, were you asking a question? Or
Clip Fanto.
Salman? Oh, yeah, I had a feeling you just forgot to mute. But it can be useful. The examples we're going to look at tonight are the typical examples we would see in a textbook or a tutorial. They're very, very generic, like the list we made the other day. We made a list and it's like, okay, that seems really odd to make a linked list because we have a linked list in Python. But ultimately, that was just so we could see the important parts of it. Then on Wednesday, we're going to start with an example where we actually apply some of these things. Probably, I'm thinking a stack. We'll make our own linked list and turn it into a stack. In an example, use because it's not that we wouldn't make that generic catch-all list like what comes in the Python programming language. If you remember from the other day when we were talking about linked lists, the only thing it really takes to make that linked list is that data, having the data field in there that points to the next one. And then we have a way to connect a bunch of things. So ultimately what we would do is make the custom object we would need and just add that next field in there so that we have a pointer going to the next one. So probably going to do a payroll example on Wednesday that uses a stack to browse it. We'll read in a CSV file and then use the stack so that things clear out of RAM immediately as we're doing it. And then we'll be able to see our usage go up and down if we check some telemetry on it. I get a hint of the benefit of it, but we won't make a generic list object and then turn that into a generic stack. We'll just put the next field and the pop method right into our employee object. So it's just our objects themselves become the list instead of putting our objects in a generic list. Our object is the list. So that's how we would use these. But before we do that in our example on Wednesday, we need to see the sort of generic version so we see what parts apply to just these things. On Wednesday, we'll do the next step with Django, which is deploying to the internet. We'll be using pythonanywhere.com. The site, we can do one free Django app there. You can pay and have more, but we just need the one free one, or it's a classroom situation. If you need more than one, it's probably best to use multiple email accounts to set up the site so you have multiple one free ones. Don't need to pay for anything in the class. But we'll look at that after our example, or we might look at the Django stuff first and then do our example, because the Django stuff will be quicker. It'll only be about 45 minutes of Django this time. So it's quicker every time, and it's a 20-minute coverage of Django. So those sections are getting shorter. We might do the Django first and then do the example after. So now I'm gonna make a step, a queue, and a binary search tree. Those are three important ones. Oh, did you say something, Samantha? Or did you just get to mute?
Sorry, forgot to hit mute.
Look at our three most commonly used ones. We'll make an example of those. We'll make those, and then do stacks and queues, take a break, then do binary search trees. Then there's more stuff about trees to talk about, and then we'll talk about hashing. In our modern world, you've probably heard of hashtags, and maybe not known explicitly where that was coming from. Oh, let me put something in the chat real quick. On this direct message that came in earlier. Okay, we might have to look at that later if you're still having trouble. That was a really I found, yeah, a question came in just a few minutes ago in emails. That's what I was answering, and a really odd error message from Docker, and I found the reason why, but not the fix, or not a feasible fix. You basically have, yeah, I'll skip that for now. That's a different thing. But yeah, you've probably heard about hashtags in our modern world, so actually talk about where that comes from and why that's so important on something as big as the data set of all the Twitter feeds. So what have we got here? So we started last week with linked lists. We kind of looked at that. It's very similar to what Python has by default. Actually, the list Python has by default is a very fancy linked list that has been building for years and is set up to be generic and cover any situation we could possibly need. We'll see in our example Wednesday, data structures kind of go the other way. Instead of using that generic linked list in Python and putting our objects inside of a list, we just use that next data field like we saw last week and turn our objects into a linked list themselves and build just functionality. I could go down a rabbit hole. I should probably stop talking there before I go too deep on something we're just introducing here. And in general, it has to do with customization and perfectly fit in our needs. That list that comes with Python is set up for any situation. It has to be ready for anything a programmer might need to use a list for. But that means there's a lot of overhead because it is very, very unlikely that we would need all of the functionality in that list, which means it's hanging out, burning up RAM that we could be using for something else, or periodically passing through the processor at a point where we could send something else through the processor that isn't just overhead not being used. So that's where we would get into customizations and stuff, but we don't do a lot of that in the classroom. And we'll see an example on Wednesday, just looking at the generic versions tonight. So linked list is an iterable collection of nodes. This definition will be important though. An iterable collection of nodes for each node contains a pointer to the next. You all have been using linked lists since your very first programming class, but it probably seemed like some big complicated thing. A list is just those two data fields we put in the example on Wednesday. The one holding the value we're going to use, and then a pointer to the next thing. That's the minimum to make a list, but some of it will make more sense when we see the next one. Yeah, it kind of looks like this. So we have element 1 has a pointer to the next one. Actually, I should make that 0. That's the indexing we're used to. So element 0 is our first one. It has a pointer to element 1, which has a pointer to element 2. And somewhere down the line, we eventually get to a null pointer. Which you've probably seen errors happen because of null pointers. But when we hit it on purpose, it's not an error. It takes a lot less processing power to tell when we get there. So when we know there's going to be a null pointer, we can use that to our advantage and make things more efficient. We looked at that the other day, and just kind of set up some custom methods. I guess might be a good time to open up that one from the other day and just kind of review where we were before we get into the next section. I think that's spider. I always forget to open that before class. It takes a couple minutes. There we go. And get the zoom buttons out of the way. Those are constantly in the way. Here's the one from the other day. So this is all it takes to make a linked list. Probably could have called that linked list. Just the element we want to store, and then a pointer to the next one. And then we'll set up whatever methods we need to use. Add stuff, remove stuff, print the list out. Probably something with indexing. because that's what we're used to doing with lists, which again would follow that same pattern. We just keep going until we hit the null pointer or find the thing we're looking for. So we'll come back to that in a moment. It's also pretty common to have a doubly linked list. Which has pointers going both ways. So we'll have element 0 pointing at element 1. But element 1 also points back at element 0. And vice versa, the second one. Element 2, which also has a pointer back to element 1. And then when we get to the end, there's a null pointer there. Or with our initial start of the list, we have a null pointer on the other end too. But that allows us to go back and forth. So we don't have to just iterate one direction. We can go forward and then backwards and go both ways on the list. Which for adding code is just like the linked list, only we have a previous data field as well. So along with next, we have it's usually called previous. We can call it whatever we want, but next and previous are nice descriptive terms. Yeah, and then I'm skipping a stack heap diagram because we saw that we saw a stack heap diagram last week, but we're getting ready to make a stack, and then before the night's out, we'll talk about what a heap is. At least talk about it. I guess that's the next one to write the definition of on the board. Stack. So a stack is a last in, first out. Structure. Items are loaded and removed as needed. So unlike a linked list where we set it up and just kind of keep it around the whole time, we saw that with the built-in Python list, the linked list, or really the list comprehensions versus the list generators. One of them loads in the data and keeps it around the whole time, and the other one only uses the current value or tries to keep the bare minimum in there. Items are loaded in and removed as needed, so it's dynamic, which minimizes our demand on resources so that other things can use those, or our software can continue to use those same resources on a different thread. Oh, which is also on Wednesdays. Yeah, we're gonna look at multi-threading. Multi-threading is really easy. It took a long time to add it to Python because of some things in the background, but once they finally got it in there, they made the foreground stuff, what we put in the text file, really, really easy. So that's going to be like 10 minutes, maybe 15 to cover that on Wednesday. Yeah, sort of a traditional thing. You can think of it as a box. We didn't cover recursion, but did something like this. So maybe we have several. Our example on Wednesday is probably going to be a stack where we process payroll. So we'll like read in the list, and I'll just write E1 for employee, E2, and we stack them all up, reading them from whatever our database is, get them all loaded into RAM, and then when we're ready to start processing it, we'll pop those. We can pop them off the list and completely remove them from RAM, so that's available again. So maybe we read in 4 things from our database, go ahead and process the first 2 of them, and then read in a couple more. 4, so E5, E6, ours won't quite be this dynamic on Wednesday, but read in a couple more, then take that one off. Go ahead and process one of them, read in more. What are we up to? 7 and E8. And the list grows and shrinks as our program goes. It doesn't just request a certain amount of RAM at the beginning of when that software starts and keep that occupied the entire time. It grows and shrinks as we need it. And then we go through there and pop things off that stack one at a time, do the processing on them, and free up the resources we're using. And there's multiple ways to do it. I guess to start with, let's just take that linked list we made the other day and turn that into and extend that into a stack so we can kind of see what's going on. So and this list holds the element we need and a pointer to the next thing. So that's enough to build a collection. So I'm gonna come down here after that and extend that a little with the stack. So make a new stack. I'll call it my stack. And it's going to inherit from my list. So we already have quite a few things in there. We need to create a constructor, as always. Hopefully that looks familiar. And our stack is just going to hold the value we want to pass in, and then we'll set up the pointer like we did before. And one other thing we need to know about a stack is when is that empty? In that picture I just drew, we start putting things on there. We add things, take things away, add some more things, take some of them away. So our stack is constantly growing and shrinking. So we need to know when that stack is empty, because that's how we know we're finished processing. So we can set up a data field in here. Well, first off, we have to pass things back up to the parent class, which is just the Python syntax that we've seen a couple times for that. Did I spell something wrong there? Yes, I did. That's not how to spell class. There we go. I don't know how to spell super either. Okay. Get those typos fixed and maybe zoom in so y'all can probably read that on the screens. So that will cover our element and build a collection. And we might want one more data field to tell when we're done. So I'll say is empty. And at this point, we haven't added anything to it, right? When we initially create it, haven't added anything. So we want to start with false, and then we'll add, oops, that's not very false. And then, oh wait, no, sorry. We want to start with true. We don't have anything in our stack. And then we can switch that to false later. That's just the conventional way of determining if we still have anything or not. Hiding's a little bit different. Well, not very different, but the big thing is we are going to use a different word. We want to push things onto our list. So if we're gonna push something onto our stack, if we push something on our stack, it's gonna go at the next available spot. So again, we'll take we need the element we want to push onto the stack. And if we're putting something on the stack, then the stack's not empty. So this is where we would check or reset that variable. So set is empty equal to false at this point, because we're not done processing once we have even a single thing there. And then really we could just call the add method. We already have an add method that will put it on the list. And in particular, this one will put it at the very end of the list. To go all the way and put it in. Our linked list was set up so that it puts the last thing that comes in goes to the end of the list. There's a couple ways we could handle that. We could put everything at the beginning of the list if it makes more sense. Just take whatever the head of the list is and push it back to make a new element, and then the current head becomes the next from the first thing. Let me put that in a picture. So there's two options. Right now, our list, if we have, say, 30 things, get our null pointer at the end. If we have 30 things, right now, our add method starts at the head of the list, goes all the way to the end, and then puts our next one here at the end of the list, and then the pointer from it gets the null pointer. That's what we currently have, but we could also, if we wanted to add something, just last in, first out, put it to the beginning of the list and set the pointer for it to what was the previous beginning of the list. That one probably goes a lot better in the picture than with words. We could go either way, but since we already have one at the end, I think it's probably easiest just to use the add method we have for the last in part, and then when we do the first out, we do our processing this way on the list. Does that make sense? So we can put it, just come to the end of the list, and then when we go to pop things off the list, what we'll do is walk until we hit that null pointer, and then use that element as the first one that we do processing on. Pop that off the stack. Then we go through. Next pass, we'll go to that null pointer, and the element that has the null pointer is the next one that gets processed. And we'll clear out our stack that way to free up the resources. I think that'll be a little bit easier to code as we do it with what we already have here. If we were starting from scratch, both of them would probably be about equivalent. But since we already have that add to the end of the list, it would take a lot of modifications, or we'd have to make a completely different add method. So it's probably easiest to do that. So then we can just call the add method. Self.add and pass in the element. And we could return something if we want. Once it's on the stack, we get an error message if things will go wrong, but oftentimes it's a good idea to return something, right? We could return true if it's successful, or false if it failed, or return some sort of number, some sort of confirmation, and then we can put it in an if else block just to make sure things are working like they're supposed to. But in this case, I think I'll just do return and not return anything, which is actually a void method. I don't think we wrote any that way. I like to do that personally. I like to do that sometimes on void methods. Return nothing, because that's what they do on their own. But if we actually put the word return there, it makes a nice little indicator that we're at the end of our method. Either that or some sort of comment end of constructor. Because in Python, white space matters. So it's nice to have a little flag or something waving so we can tell where the end of a method is if we start hitting white space errors. So I should add things to the list. Then we need to remove them from the list. And the remove method we have earlier, we were looking for or from last week, we were looking for a specific element, but that wouldn't necessarily be a stack. A stack really it's in that second half there. We process it in a certain order. The last thing we put in is the first one we went out. So we'll define our own pop method. So, and we don't have to say what it is. We just need to get to the end of the list. So current is going to be self. We'll start at the head of the list. And then while current.next is not null, or sorry, none in Python, means the same thing, but in most languages we type null. It makes more sense with the word they went with in Python, but yeah, if the next element is not empty, then we know there's something there, so we'll just keep walking until we get there. Say current is going to be current.next. Whoops. I don't know why the emojis popped up there. I don't need to type emojis in the code. But whenever that statement is false, so when we do get that null pointer, the thing that just the next data field is just holding the value none. That's the next one we want to pop off the stack. So we'll return current dot element. Because at that point, we don't need to worry about the next pointer. We know where the next pointer is going. We just want the element from it. And then we get that back for the current processing method. I think the representation method that we inherit from list will work for us here. So just a little bit to extend that into a list, and we can try it. I'm going to move this stuff over to a different file. So I'm going to take all that list stuff we set up the other day, and I'm going to cut that and put that in a new file. Import structures. Yeah. And then paste that in, or actually from structures, import list, or my list. There we go. I'll do that one so I don't have to change the code. So that's the example from the other day, and we'll move things over here as we get them. And then and this one we'll just do the current test case, and that way we don't have 20 lines printing out by the end of the night tonight. So ready to do a stack. So S1 is going to be in my stack, and we need an element to start with. Actually, I want to change this up a little bit. So I'm going to say my stack and pass in none, which is exactly the same as if we would have left that empty, except it won't get mad because we didn't send in a parameter, or we didn't fill the parameter, we didn't send an argument. And I'm going to, when we change this right here, whenever we go to push something on the stack, let's check and see if the stack is empty first. So if self.element is equal to none, that means we haven't done anything yet. We need to create our element here. What I wanted to do? Sorry. Yes. Actually, I'm going to take this line. Can I put this line here? Yeah. So instead of putting this in the constructor, I'm just going to create the list I'm going to create the stack as a completely empty thing. And if we don't have anything in there, so if the current element is none when we say push something on the stack, then we will call that super constructor and then just say return. We haven't wrote any code this way yet this semester. If you stare at that code for a moment, anybody tell me a difference between that and an if-else block?
Something there, function's gonna break.
Yeah, the function's gonna break, so that means we'll never hit this part.
Yes.
So that's essentially like an if-else block. Actually, this one processes a little bit quicker. This is more efficient than an if-else block, but that's an alternative way to write if-else, which is really nice when you're in the curly brace languages, because that'll cut out a whole bunch of curly braces, which are easy to miss. But that's we haven't seen that yet this semester. So this is basically an alternative way to write an if-else block, to do returns in both of them. So we'll create a list, and we'll just always make our list empty to start with. Then whenever we add an element, well, if the list is none, then we do want to do self dot is empty to true. Oops. Not true. Is empty is going to be false. Sorry, that threw. Yeah.
What's super element?
So super calls the parent class. So that's going to call the constructor on my list, which is the one up here. So it's going to pass in the element and create that element in the list that we're turning into a stack along with the null pointer. Make sense? Okay. So yeah, super is the keyword to call the parent object. Self is the keyword for the object we're making, right? See, we don't even have to have self dot anything. We might want to refer to the object itself. And super is just the keyword that calls the parent. So we can access anything from the parent that way. And notice that is mangled. So we can access the mangled stuff in the parent that way by using the super method. Push and pop, that'll get us stuff on the stack. So now that we have that stack created, we need to push some stuff onto it. So like S1 dot push a 5, S1 dot push a 7. Then we probably want to print that. Let's see what S1, print S1, see what's in there. S1 dot pop, hopefully that's going to remove that last variable and send it back so that we can do stuff with it. So we want to put it somewhere when we get it back. And then if we print the list again, it should be shorter. As long as I didn't make any typos. Because typos happen when we're just typing and I'm up here talking and typing at the same time and changing my plan as we go. There's more than one way to build these things. So that's why we want to look at it in the generic sense first, just to see what those key parts are. We need some way to add elements to a list or a tree. We can turn we need something else to turn into a stack. A stack is really a processing method. It's not a thing itself. So here we're turning a list into a stack, which we refer to them both as nouns when we're talking, but really what we're doing is stack is the verb that we're applying to the list noun, if that makes sense. Give this a trial run, see what happens. Yes, in the chat message, a different way of referring to that. That's a pretty common thing. So when you see examples like that code, sorry, I didn't see that pop in the chat room the first time. When you see examples like that, there's returns in both of them. So this code would never get reached if we go into when we go into that if statement. Let's give that a run, see if it worked like it was supposed to. Nope, something went wrong. My stack in it takes one positional argument. What? But two were given. Oh, sorry. Oh, that's a great thing. So I forgot to take that out after I removed the argument. I removed the parameter, which means we don't have any parameters left. But look at that message. Two were given. So there's the one we passed in, but this was also passed in as a parameter. It's in a different spot altogether, right? It's not inside the parentheses, but we can see from that error message that the Python interpreter is counting S1 and none as a parameter. But the only one we need is something to fill the self parameter. We hit Control L, clear that out, and give that try that again. My stack object has no attribute element. So this one we talked about in the section on object-oriented stuff. Does anybody remember, think back, remember, was it 3 weeks ago? 2 weeks ago? They blend together after a while, right? Somebody asked for a date on a video, and I was like, I think it was last Monday and the previous Wednesday, but it might have been the Wednesday and Monday before that. We're at the point of the semester where the dates all start to blend together, but if y'all remember talking about object-oriented programming and inheritance. So we inherited stuff from my list, which has a couple of data fields and then a bunch of methods.
We don't initialize the stack until push. That's why.
Something like that. It has to do with initialization, but we would say that a little bit different in terms of inheritance. Here, let me open up the example from inheritance. Go to files and wait, why isn't that showing all my files? Go up a level. And where's our object-oriented stuff? Zoo. So here was our object-oriented example. Remember how we had all, right? We have these data fields. We went over the class variables. We do call, that's the term usually used. Our instance variables, because it's just easier to say in Python, or it might also say data fields, but and our mangled variables. But then we made all of these things, right? We had all our getters and setters. Do you remember why we had to have our getters and setters? And then down here, we didn't, like here for the get name, we didn't use self.name. We went with self.getName instead. I couldn't hear you.
Because they're mangled?
It has to do with the mangled, but even on our non-mangled ones, we don't inherit data fields. We don't inherit variables. We only inherit methods.
Yes.
That for an analogy, think about people and parents, children and parents. We inherit the behaviors our parents taught us, but not the experiences that taught our parents those behaviors. Does that make sense? So we don't inherit data fields. We only inherit the methods. So this element, we don't actually have access to it. We can call super dot element, but let's do a better form. So for better form, let's come up here and add getters and setters into our so like get element. Oh, that just needs to return the element. Return self.element. And we might also want set element so we can start doing things with that variable. And that just assigns the value something. Self.element equals whatever we pass in. Since the one that belongs to the object has self beside it, there's no ambiguity. Those words only look the same to us. They will not look the same to the computer. So we can just use that. But some people, it does kind of bother to use that same word multiple times. So you could just call your parameter E. But we need to pass in some value to reassign to that. Same thing on the next field, because we're going to need that here in a moment too. That's if we fix this one and then hit run again, we'd immediately hit the error message about next not being accessible. So let's do getter and setter for that. So get next. Oh, we don't need any parameters because all we're doing is returning the next value. And if we need to set it, oh yeah, and then the technical term for these are accessors and mutators. You will only ever see that on multiple choice quizzes like certification exams. If you were working on a team of programmers and actually use the term accessor or mutator, they'd probably look at you like you were weird because we call them getters or setters, unless we're taking a formal certification exam or something. Where they are accessors, we want to access that value, or mutators, we want to change that value. And a mutator, obviously, we need to know what the value is changing to, so there's a parameter on that one that will need filled. That's an important one and an easy one to forget because once we make the object, we can access it directly. But the children do not inherit the data fields. They only inherit the behaviors, the methods. So down here, this self.element needs to be get element. This one is local. That we're just passing back up. Is empty is local. Self.add, that's a method. We inherited that, so that's good.
We still didn't initialize, so it wouldn't inherit the method, I guess.
It'll be initialized. We're just it will be initialized with none. So when we start, yeah, that's this if statement. So it will initialize it, but since we haven't called the parent constructor yet, the Python interpreter is going to do that in the background. It will automatically put none in it as a parameter, like what I typed explicitly at first.
When we do the class by stack by list, that's when it hits the methods.
Yes. Yeah. And then it initializes it at this point, and then we fill the values in later. So we're doing the same thing. Normally we do it in the constructor, but we're just doing the same thing down here later.
So the super part, that's when the data fields are inherited.
That's where we actually, we already have the data fields at that point. This is when we start to fill them in. So at this point, they all have none in them. We have that element, but it has none in it. So this is where we actually put a value into it. The spot is reserved in RAM, and this is where we actually go ahead and put something in that spot we store. The spot we reserved over on the RAM chain. And then on the next one, we're walking through things. So current is self, but we don't have access to current. Actually, I can throw that error message again. Let's throw that error message. Let's see what this error is. My stack object has no attribute element. Oh, I missed one of them. Where did I miss that at? here. My error messages came out of order. This is going to be a get element method again. Oh, there we go. Oh. Same line. UI line 19 and get element return self.element. I was not expecting this error message. What's line 19? Oh, that's all right. I do need this line. And we'll just pass none at this point. See if that likes it better. There we go. Oh, it didn't remove our element from the list for some reason. I'll look into that, and I was expecting another error message. That's probably why. Because here it's like we're trying to access that thing. Really, that should be self.current. So we want that to be self.setCurrent. Open some parentheses, get rid of this stuff.
Don't have a set current, I guess.
No, wait, sorry, my mind is elsewhere. Current is self, yeah. That line is fine. Because current is a local variable. Then this one, current dot get next is none. Then current is going to be current dot get next. So just replacing those data fields with the other one. And I got a little bit confused there. I think that one probably had to do with, I've been here since 8:30 this morning. It's been a long day. But does that make sense? And see how we had to use those methods instead of the variables. Why didn't it remove it? Return current dot get element. And it's still in the list though. We haven't actually taken it out of the list, right? So instead of just returning that immediately, I'm going to put it somewhere. I'll just say temp, our normal variable for temporary. We'll grab that element, store it somewhere, but then we need to remove it. We'll say current, oh wait, self.remove. Self.remove the thing we're looking at, which is going to be current.get element. Is it not removed?
Current has 2 U's.
Ah,
Single R.
oh, 2 R's. Yeah. There we go. Spell words correctly, it works better. So we want to remove that from the list, and then we'll return the temp one. Okay, sorry. That was lots of typos. Okay, there we go. I think I need more caffeine. Whenever we take a break in a moment, I'm going to go drink a whole Mountain Dew really, really quick and see if that wakes me back up. So see how it's no longer in our list. Our list grew short. Our stack started to grow. Then we did some processing so we could do something with that 7, right? Excuse me for a second. I forgot I was sitting somewhere the other day with only this computer on me and installed Teams. I did have Teams uninstalled here. And I need to close that to make sure there's no confidential information. Luckily, that one just said thanks. Confidential information passed by on the earlier. But I don't need to be doing a screen share and a recording on places where confidential information might pass. All right. So normally we would do something with that 7. So we print twice as much as the top of the stack is plus cast as the string 2 times x. Right. We do something with that element when we pop it off. So we're doing our process, all the processing we need with it, but we're done with it. It's no longer hanging out, taking up RAM. We will see a much better example of that on Wednesday to see how we finish that list. And then we can keep going. Right? It's like, okay, we're done with that. So let's just say while S1 dot is empty. Actually, I forgot a word. While not S1 dot is empty. So while it's not empty, or you might want to change the method name or the variable name just a little bit to find whatever makes the best sentence to read there. But while our list is not empty, then let's just pop some stuff off. X equals S1 dot pop and print S1. And we'll keep going until it is empty. And then whenever we're done, right, by the time we finish this list, whenever we do get to that is empty variable, we did set it back to true, right? We never did set it true anywhere, did we? We'll pop while current dot get next is not equal to none. So we go all the way to the end. I guess we better set that check and see when the list is empty. If current dot next is not none, eventually we'll hit the very last one. Actually, we can probably do it up here. If current what would be the best way to do this? Any thoughts? We need to check and figure out where our is empty gets set true. So we'll grab the first one. We'll probably check this way. So if current dot get next is equal to none, we might just want to return this element, right? Because if this is the only thing in there, that means we're empty. Return none. Or return
If we get next, then we may still have one element.
current dot. Yeah, so we might have this one, so we want to return the element from here. And before we return that, we can go ahead and set that Boolean to true. Self dot is empty equals true. Because if we're at the very beginning of the list, right? We set it to self, we're at the very beginning, very bottom of our stack, then the next element will be none. There's not anything else in the stack. We'll set that is empty to true and return this, and we don't have to worry about removing it because we're getting ready to delete it when we're done with the stack anyway. But then our list, we'll know our list is empty. I guess for good form, we could kind of follow measure of what we did earlier. Temp equals all of this. That way they're consistent. And then we'll say current equals none. So now our list is completely empty. It is actually empty and we'll return 10. Using this as an example, that's probably a better form because it just matches what we did earlier. So it's just that very first element because it didn't fit the pattern that everything else will. We'll get back there and we don't necessarily empty it out. Right? Because everywhere else we're checking if current is not none. But on the very first one, we have to check if it is none. That makes sense to everybody? So now we should be able to loop through there. And before we do that, let's add some stuff to the list. Make it longer. So S1 dot push on a 3, S1 dot push a 23, push onto that stack at 33. That way we got a few things on there. And we'll see our list grow and shrink as we go through here. But notice we didn't enter an infinite loop either. We did eventually hit the end of the list. I guess we should probably print here. Before we start doing that loop, there we go. So we started building a stack. Notice how our data set gets bigger and smaller as we go with just a couple of keywords. So by the way, we do have push and pop in list built into Python, but we're going to use this in our own custom data class in Wednesday's example. That's sort of the idea of a stack. Oh, this one, yeah, I'm getting ready to go to a break, so I can put that on there right now. Actually, I can probably move that over. We don't need space in the other one. So yeah, it's just printing out 2 times the thing instead of doing that somewhere else and then storing it in a variable and then casting that variable as a string. I just did it right in the cast to string method because it will do the calculation and then send the result as the argument to fill the parameter. So kind of like order of operations. The idea of a stack makes sense there. Basic elements. It will make a lot more sense when we see that in an example, and hopefully when we see a stack in an example on Wednesday, that'll help the other ones we're going to look at make sense too. I guess we could do a queue. Next up is a queue, which will go faster because it's very, very similar, except that we go through our list the other way. It's not written on the board. It's a first in, first out, like the line at McDonald's. But now is probably a good time to take a break, right? Take our first break because yeah, this is going to be our long night. I told you all in advance, and so probably going to take a 10-minute break now, and then we'll take 2 5-minute breaks later. Or it's going to be a long night, man. We might take another 10-minute break and then another 5-minute break as well. 10 minutes sound good to everybody? All right, my laptop says 7:05. We will get back to it at 7:15. I'll see you in just a moment.